Not ready to use the devices quite yet. Just keep them warmed up, keep them handy. We'll be graphing on that same sheet one last time. And so you'll make a third tab and do that final graph, and then we'll be done with those. Quick review that we've gone through exponential growth, which is what every population we've ever seen does when they have all the stuff they need. We've talked about logistic growth, which is what populations do when they've started exponential, but then reality has kind of caught up with them. Some limiting factor, we gave that a name, a limiting factor has caught up. And then we looked at growth that is more realistic, logistic growth, that it's not that they really look up and see the carrying capacity coming and slowly start having less babies. What really happens is they overshoot it, right? They overshoot it and there's a mini crash. A bunch of critters die and then they're under it and then they overshoot it again and they tend to bounce. So real logistic growth tends to bounce around that number that we call the carrying capacity. Any environment has a specific carrying capacity for any population. Everybody good so far? Okay, so here's a graph. And you tell me what you think, what kind of growth that fits most closely with. Don't draw it yet. Which curve is that?
Realistic logic.
Last one we did, right? Realistic logistic growth. Now, let me give you, in the same time frame, in the same environment, a graph of a different population. Now take a look at that graph and tell me what story that graph is telling.
The yellow line, like the prey, and like the pink line, the predator.
Ooh, I like it. Yellow line is prey, pink line is predator. That's exactly right. And this is actually a very specific situation in which the predator had been gone from Yellowstone National Park for at least 50 years. Wolves. Wolves have been eradicated like they have been from here. There's no wolves in Ohio. There were no wolves in this huge wild space, Yellowstone National Park. And then at a certain point, the Department of Wildlife actually reintroduced. They took a pack of wolves from Canada and reintroduced them in Yellowstone National Park. And ecologists had kind of lobbied for this for years. And there's a pretty strong hunting lobby as well, of course, that hunt elk, who kind of freaked out and said, no, you're going to destroy the elk population if you let wolves loose in here. And at first, yeah, everybody was kind of freaking out because the wolves started to increase in population and the elk definitely crashed. And the ecologist said, wait, give it a minute, right? Give it a couple of years. And what happens is the wolf population tops out at its carrying capacity, the elk bounce, and in fact, the elk wind up in a slightly healthier state, at a slightly higher population than they were pre-wolves. Why do you think that might be? Why would hunting actually be a good thing by wolves for elk? Interesting. It definitely did change their behavior. They started hanging out in different parts of the park, parts that had more tree cover instead of the open fields. What else? What about evolution? I think you're on the right track. So one of the principles in evolution, natural selection, you know better, I think, as survival of the fittest. What might be true of the herd of elk before and after wolves? Which elk do you think wolves get when they hunt elk? They pick off the weak ones. They pick off the sick ones. And they get the really young ones sometimes too, which isn't great. But that's kind of how it works. And so, yeah, you can pass back. Okay. So yeah, hunting by a wild predator can actually sometimes be beneficial to a herd. Go ahead and draw that as precisely as you can. Make sure the curves kind of mirror each other, because that is your tip off. Whenever you see a graph like that, it's predator prey, when they mirror each other exactly like that. Because of course, when one's doing well, the other one's not. Okay, so we've been using the term limiting factor for kind of what's the first thing, and obviously in this case, the limiting factor was definitely predators that these elk ran into. The thing keeping that population lower than it could be is definitely the wolves. And so we need to differentiate now. We kind of categorize limiting factors into two groups. There's the kind like predators that it matters how crowded the population is. The wolves had it easy for a while because the elk were everywhere, right? The elk had a lot of crowding in Yellowstone National Park, and so they were easy to pick off for the wolves. And as the elk started to thin out and maybe change their behavior a little bit, then it was harder for the wolves, and the rate of predation went down. So a limiting factor is really any condition that is keeping a population size from increasing. And predation is a limiting factor that we define as density dependent. Population density, which is what we're talking about. What's the state in the United States with the highest population density?
New York.
It's not New York. Most people think that. It's not. It's a good guess. It's a very good guess. It's not California, because California has, wild areas that aren't as densely populated. No, that's real low. That's like, Mexico City, yeah, if it was a state, would win.
What is it, New Hampshire, like the really small one?
You're thinking in the right direction, the right part of the country and the right sort of size of state. Now you're dancing right around it though. I'll give you a hint. It's where all the people in New York, where all the people that work in New York actually live. Chris? It is New Jersey. New Jersey is the most densely populated state in our union. And so clearly this isn't about size, right? Texas doesn't win this. It's not how many people. It's how many people what?
Area, but like, there's a different word for that.
It's a unit of area. We'd be saying how many people per square mile or square kilometer. Yeah, absolutely. It's not how many people, it's how crowded those people are. Yeah? So that's what this is. A density dependent factor like predation is worse on a population. It's harder on a population when they're more crowded. That's all. What else besides predation would count? Can you think of something that's worse for a population, that's more of a limiting factor when they're crowded? Absolutely. Competition gets much stiffer when the population is crowded. Anything else? Another big one. It's going to seem like you're going to kick yourself when you don't get it. I mean, that is one for sure. How about disease? Yeah. That's why we all get sick in the winter more, right? Because we're all packed inside more. Well, it's one of the reasons. So yeah, these affect population more seriously as density increases. We're talking competition, predation, parasitism, disease, things like that that are worse when it's crowded. So what's the other kind going to be? There's density dependent. There's going to be density independent. What do you think that would be? What would be a limiting factor that it doesn't matter how crowded you are? The weather, like what? A volcano erupting is a perfect example. Like white hot molten lava flow doesn't care if you're crowded or not. It's going to kill what it kills no matter what. That's absolutely right. Anything that you could qualify as like a natural disaster kind of thing is going to count as density independent. Its effects are not dependent. A flood, a fire. A hurricane. People. I mean, yes, if there's more of you in the population, it'll kill more of you. But the crowding doesn't matter. So that's something you'll be asked to do, is to sort between density dependent, density independent limiting factors on a test. That is a task you'll have. Or to describe the difference. All right, time for your last population graph. Go ahead and get your device out, get your sheet out, and create a third tab, please. Does anybody need that predator prey graph back? I noticed I was pushing a little bit. Anybody need that slide up? All right. Now, this one's a little different. You're not gonna be able to use any tricks. So you'll have to type all these in, and you'll need to pay special attention to where the decimal is here. Notice we don't get above 1 until there. All of these are point something, so make sure you get that correct. But otherwise, same as always, you select the whole thing and graph it, see what it looks like. You got a graph? Make it a line graph. I'm not sure if it defaults to that or not. First of all, which kind of population growth are we looking at? Like, of the ones we've learned, what is this? Am I? Is it? Are you seeing a level off spot where it starts to bounce? Your graph must be different than mine. See, now that looks pretty straight up over here. What do we call that? That's exponential. Yeah, there's some rocky stuff at the beginning. Here, right? This spot here. But what you're looking at turns out to be the actual human population growth curve. Since, since the turn of the modern age, right? The common era, I think what we call it now, we used to say AD. And so this is basically an estimate of what the population has been for the last 2,000 plus years. And it ain't logistic yet, right? We got clearly we're in exponential. Should we check the population now? You want to add another point? Why don't you put it in 2020 on your, and it should live update your graph when you put that data point in. And let's take a look. Let's add one last data point. Census Department has an estimate. Okay, so world population is what we want. And let's call it let's round up just a touch here, 7.7 billion. So that's what this is, your numbers in your right-hand column are billions. 7.7, put that in, and it should add it to your curve. So does that give us some level off if we hit the carrying capacity? No? So if anything, it's like, it makes the curve a little more vertical, doesn't it? It looks a little more straight up and down now. Yeah, we are in the thick of like the big time boom of exponential growth. Why don't you, in your notes, go ahead and write down today's population number, and let's write it down. Okay, put today's date, which is the 20th? 10/20 at 7:56 a.m. And let's round off our number at 7,691,401,100. 7,691,401,100. And if you remind me tomorrow, we'll check in and see how many people we've added to the world in 24 hours. Keep in mind, this number, as it goes up, is not just the number of people being born. It's the number of people being born minus the number of people dying, based on all the birth rates we know across the world. It's not perfect. It's not like they have cameras in every household, right? But it's based on pretty solid math. So that is what we are going to spend the next day or so talking about: human population growth and how and why it went exponential. And then that kind of bleeds into chapter 6, which is this incredibly kind of high booming population of humans and how that is affecting the ecosystems of the earth that we depend on. But I want to give you some work time. You've got guided reading that's due tomorrow, so I'm going to go ahead and let you dig into that. If you can do that, I'm happy. If not, we can keep going here.